Okay, I think we'll get started. So it's my pleasure to introduce today's seminar speaker, Dr. Nina Fedoroff. And Nina is visiting us as part of the Storer Lecture Series. And as most of you probably know, but if you don't, I'll tell you, the Storer Lecture Series has 2 lectures. This one this afternoon at 4:10, which is meant for a broad audience. The title has been changed, but been made more concise by Nina. It's Sustainable Agriculture for 9 Billion, the first half. And then she will talk also tomorrow at 1:10 in the Life Sciences Building in 1022. She'll talk more about her research. That'll be a research seminar tomorrow. So I'm not going to go through Nina's full history because it's extensive. I'll just tell you a few things. Nina has her PhD from Rockefeller University. She worked for a fellow by the name of Don Brown, who was a xenopus biologist. Yeah? At Carnegie, okay. I see, with Zinder, okay. Well, when Nina went from her PhD to the Carnegie and worked for Don Brown as a postdoc then, yeah. And Don Brown works on xenopus.
And Doug worked for me as a postdoc.
And I worked for Nina as a postdoc later on. I used to argue with Don. So anyway, Nina has a number of claims to fame. The thing I recall in particular was when I joined the lab, Nina was working on May's transposable elements. She was working on ACDS and SPM. And Nina inherited that legacy from Barbara McClintock and spent a large fraction of that portion of her career actually working directly with Barbara and became sort of the heir apparent to the research that Barbara had done and carried that along for a number of years. In the early 90s, she left the Carnegie and went to Penn State University, where she was the founding director of the Huck Center, Huck Institute. She has continued to do that. Now, since then, in fact, prior to that, Nina was elected to the National Academy. She's, in the early part of this last decade, received the National Medal of Science. She's been the science advisor to Hillary Clinton, or to Condoleezza Rice during the Bush administration, and also had served in advisory capacity to USAID, and continued on as a science advisor to Hillary Clinton under the current administration. So she's had a wide range of experience, both in terms of formal science at a high level, advising national policy. She's currently the president of the American Academy of Sciences and American Association of Sciences. Yeah, AAAS. Thanks, Nina.
AAAS that publishes science.
That's the one, the AAAS that publishes science. So she's had a wide range of experience, and I think she'll bring those issues to bear when she gives her talk this afternoon. So, Nina, it's my pleasure to welcome you.
Thank you. I'm delighted to be here, and just to make the issue a little bit more controversial, there's another part of my title. Now, in early January this year, I got a note from Andy Revkin of the New York Times saying, talking but this does not have a clip. Okay, we're just going to park it here and go on. But let's put this in perspective. Concerns about food security are old as mankind. Thomas Malthus's eloquent 1798 essay on population crystallized the dilemma for modern times, so much so that Malthusian has entered our language to denote a population-based food scarcity. Malthus argued, of course, that humanity was doomed to poverty and famine because the human population grew exponentially, while mankind's ability to produce food could only increase at a linear rate. Now, oddly enough, it was about the same time that he was writing his essay that science began to enter agriculture in earnest. With Joseph Priestley's discovery that plants evolve oxygen, he used a plant to keep a mouse alive in a sealed jar. Now, since then, science and engineering have powered enormous gains in agricultural productivity through fertilizer production, plant breeding, mechanization, largely during the 20th century. Particularly important were the inventions of these two German scientists, Haber and Bosch, who developed a method early in the 20th century for converting atmospheric nitrogen to forms that plants can use. Nitrogenous fertilizers are now synthesized in huge plants around the world, and that's part of the reason we have as big a population as we do. Another important development, of course, has been the mechanization of farming. Today's most advanced precision agriculture is indeed technologically sophisticated, using GPS-guided, increasingly driverless tractors, materials such as these plastics to retain soil moisture and control weeds, and complex integrated pest management strategies. But even before science and technology entered the agricultural arena, humans had made some spectacular progress in the genetic modifications of plants to make them better food crops. Corn, which is also known as maize, came from this grassy relative called teosinte. Corn and teosinte are so different that they were originally assigned to different species. And yet these two plants are so closely related that can be crossed, and the offspring are everything from what looks like the teosinte rachis, with its hard as rock seeds, to small and medium-sized ears of what is recognizably corn. Over thousands of years, people have converted this grass to one of humankind's most productive crop plants. But the truly dramatic expansion of the ear took place largely in the 20th century, when it was discovered that seeds from a cross between two highly inbred, rather small and weak plants gave much more vigorous plants with much bigger ears in the first generation. This, of course, is what we call hybrid vigor, and it's the basis of our currently extraordinarily productive corn varieties. Now, we've done the same with wheat. Modern wheat is, in fact, an interspecific hybrid and polyploid with 3 different genomes. And we've done the same with rice. They're almost unrecognizably different from their wild relatives. Now, when Malthus penned his essay in 1798, the human population of the world was about 1 billion. Science-based agriculture supported a tripling of the global population by the middle of the 20th century, and another doubling in the second half of the century. Now, remarkably, the fraction of humanity suffering from chronic hunger declined from 1/2 to 1/6, even as the population doubled from 3 to 6 billion. The bad news is that success has come at a huge price, and I quote Peter Raven, retired director of the Missouri Botanical Garden and inveterate champion of biodiversity. He says, nothing has driven more species to extinction or caused more instability in the world's ecological systems than the development of an agriculture sufficient to feed 6.3 billion people. You can see the quote is a little old. We're at about 7 billion now. The planet's forests and prairies have given way year by year and decade by decade to much simpler agricultural systems virtually everywhere in the world. Complex ecosystems have been replaced by monoculture, often irrigated with fossil aquifers, water pumped from the ground that is not replaced. This is where we are today. The loss of biodiversity is already at catastrophic levels and continues to accelerate. Moreover, it's not confined to species on land. The overuse of fertilizers has resulted in the eutrophication of rivers, lakes and coastal waters, making water uninhabitable for many aquatic and marine organisms. The population pundits are now telling us that we can expect another couple of billion people to be added to the human population over the coming decades. The UN just released its latest population projections, and it's actually looking like 9 billion might be an optimistic guess. As the report says, small variations in fertility can produce major differences in the size of populations over the long run. The high projection variant, as you see going off into skyward, whose fertility is just half a child above that in the median variant, produces a world population of 10.6 billion in 2050 and 15.8 billion in 2100. Here's a sobering factoid. The amount of arable land has not changed appreciably in more than half a century. This looks like a huge increase, but it's only 10%. Meanwhile, the population has doubled, which means that we've gone from about an acre of arable land per person to half an acre. And despite pockets here and there, the overall amount of arable land is not likely to increase much in the future because we're losing it to urbanization, salinization, and desertification as fast or faster than we're adding it. So doubling the food supply by doubling the amount of land farmed is not an option. And then there's climate change. We're rapidly moving out of the temperate range in which we domesticated our current water-inefficient temperate crops. This little X here is the very hot summer in Europe of 2003, when 50,000 some people died. What we didn't hear about is the 30 to 50% decrease in crops. I see people shaking their heads, yes. No one read about that in the newspapers. Now, if the climate scientists who are looking conservative at this point are right, this is going to be an average summer in a few decades and a cool summer by the end of the century. 2010 was not kind, but is this climate change already? Russia endured its hottest summer ever and banned wheat exports. Even before the floods, farmers in the Punjab had incurred losses to their wheat harvest due to the intense heat wave, with the hottest temperatures ever recorded in Asia as high as 128 degrees Fahrenheit, which is 53 plus degrees centigrade. As if the heat wave were not enough, it was followed and accompanied by extraordinary flooding in Pakistan, China, North Korea, Vietnam. Since then, we've seen extraordinary floods in Australia and now in our own country. Is this climate change yet? Well, the climate scientists are always a bit cautious in making a causal connection between any single extreme year and climate change. But the extremes we're experiencing last year, this year, are precisely what they predict. In fact, Jim Hansen has a very gripping book out called The Storms of My Grandchildren. I think it's something like that. Don't remember it exactly. Well, crop yields decline with increasing temperature for several reasons. An important one is that photosynthesis, the process by which plants turn solar energy into food, has a temperature optimum in the range of 20 to 25 degrees centigrade for our current crops and declines at temperatures much above 30 degrees. That's a mild 86 degrees Fahrenheit. Heat is often, although not always, compounded by drought, as we've witnessed in Russia. Climate scientists predict that many of the Earth's most populous places will become drier, as indicated by the red circles. You can see from this critical table from a yet unpublished science paper by Nobel and his colleagues, one of the first groups really working on assessing the impact of climate change that has already happened. This is an analysis of the impacts of temperature and precipitation trends. And you don't need to look at the details. You can see that it's largely negative, although compensated slightly by the effects of higher CO2 on rice, wheat, and soybeans, all C3 plants. These are certainly not trends that'll help us double the food supply. So here's what we need to do in the 21st century to even begin to come close to the notion of sustainable agriculture. We need to reduce agriculture's ecological impact, its pollution of air, land, and water. We need to reduce its demand for fresh water. Some 70 to 80% of fresh water is still being used for farming. That's as true here as it is elsewhere. We need to adapt staple crops to a hotter, drier world in many populous places. And oh, by the way, we need to double the food supply over the next couple of decades. Well, the good news is that over the past half century, we've developed the knowledge and the technical toolkit to tackle these daunting challenges to expanding food production in the face of shifting climate. The late 20th century witnessed a genetic revolution with the invention of recombinant DNA technology, the explosion of genome sequencing, and the development of techniques to reintroduce individual genes into plants and animals. Today, it's possible to use these techniques to modify crop plants and domestic animals very precisely through adding, removing, or modifying genes to improve their productivity and protect them from pests and pathogens. One of the most familiar examples is the introduction of a bacterial toxin gene from the soil bacterium Bacillus thuringiensis into a variety of plants, conferring resistance to important lepidopteran insect pests. Another example is altering the pattern of growth hormone gene expression in salmon to increase productivity by increasing their growth rate, yielding more fish for the same amount of input feed. You've all undoubtedly read about this. The bad news is that there is widespread suspicion, even fervent conviction, that crop modification by the contemporary molecular techniques is somewhere between immoral and downright dangerous. This has resulted in the prohibition of growing such crops in some countries and very stringent regulatory regimens in other countries, including our own. As Professor Rob Parlberg explains in his book titled Starved for Science, how biotechnology is being kept out of Africa. Europe's anti-GMO beliefs influence Africa in many ways, ranging from the funding of anti-GMO NGOs such as Greenpeace to the threats of trade embargoes. Parlberg relates that in 2002, with drought in Zambia creating a dire need for international food aid, Agriflora, a private company in Lusaka, Zambia, that produces vegetables for export to the UK, received phone calls from UK supermarkets that their exports of organic baby corn would be in jeopardy if food shipments containing GM maize were allowed in Zambia. The growers asked President Mwanawasa to reject the food aid. He did. It's a dramatic story, but not a unique one. Today, only South Africa grows GM crops on a commercial scale, although several countries are getting closer, including Egypt, Burkina Faso, and Kenya. Fortunately, molecular modification, GM technology as it's often called, isn't dangerous. The European Union has invested hundreds of millions of euros in research on the biosafety of GMOs. As you can see in this quotation from the recently published overview of the last 10 years of research, and they, by the way, refer to the previous 15 years, which is summarized in a separate publication, quote, "The main conclusion to be drawn from the efforts of more than 130 research projects covering a period of more than 25 years of research and involving more than 500 independent research groups is that biotechnology, and in particular GMOs, are not per se more risky than, e.g., I don't know why that's in there, than conventional plant breeding technologies." End of quote. Now, every credible scientific body that has examined the evidence has come to precisely the same conclusion. And yet, paradoxically, the popular mythology has it backwards. Now, the rest of the Raven statement, from which I quoted earlier, reads, "To assert that GM techniques are a threat to biodiversity is to state the exact opposite of the truth. And the oft-repeated claims that transgenic crops threaten biodiversity. Rather, it's precisely the biologically based genetic modifications that offer the best hope for simultaneously increasing crop productivity on land we already farm, while at the same time decreasing the impact of agriculture on biodiversity by decreasing the use of plows, fertilizers, and toxic chemicals. And despite continuing controversies in anti-GM activism, GM crop acreage has increased incredibly rapidly worldwide, driven, unfortunately, primarily by cotton, corn, canola, and soybeans. In 2010, GM crops were grown in 29 countries on 148 million hectares. You have to multiply that by 2.5 to get the acreage. That's an 87-fold increase since 1996, the first year of commercial planting. More importantly, and this is really the important point, 90% of the more than 15 million farmers growing biotech crops are smallholder, resource-poor farmers, in spite of all the junk you see on the internet and in the press. The simple reasons that farmers migrate to GM crops is that their yields increase, somewhere between 5 and 25%, and their costs decrease, in some cases by as much as 50%. Someone asked me today about the truth of the the urban legend that farmers that are growing GM cotton in India commit suicide, and that is exactly the opposite of the truth. There's a recent study that the International Food Policy Research Institute has done that essentially they went and interviewed people, and it turned out that it was the growers, the farmers that were able to adopt the GM technology that were doing better. Now, unanticipated adverse effects, of which many were predicted, have not materialized. The only unanticipated effects have been beneficial. For example, the use of insect-resistant plants has reduced pesticide poisoning of people. Now, pesticides are applied quite safely in the highly mechanized agriculture of the developed nations using climate-controlled tractors, but there are some 25 million cases of pesticide poisoning every year in less developed countries where farmers often have little protection from it. Moreover, pesticides kill a broad spectrum of insects, both harmful and beneficial. Using Bt crops means more insects and more wildlife, such as birds, that can thrive along with the crops. And a long-term study published recently in Science shows that the widespread use of insect-resistant crops in the Midwest has decreased pest pressure in the entire area, benefiting non-GM crops as well. It's also been observed in China, reported from China and India. And there are also health benefits. Contamination of grains, including corn, with mycotoxin. These are very toxic compounds and carcinogenic compounds made by fungi. It's an ever-present problem. Contamination by mycotoxins of Bt corn is lower by 2 to 10-fold in different studies compared with non-Bt corn. This is because the fungi that follow the boring insects into the plants can't get in. No insect holes, no fungi, no mycotoxins. So what's the problem? The problem is that after all these years, and given all the promise of molecular methods, we have virtually no GM crops other than cotton, corn, canola, and soybeans. The first of which is a non-food crop, and the rest are, to a large extent, animal feed crops. Even the long-awaited golden rice is not yet available to farmers. Developers Ingo Petrikis and Peter Beyer were able to get companies holding the patents on various genes they used to agree that the rice could be made available to poor countries' farmers without charge, and they were able to do that in a matter of months. But although golden rice has been ready to distribute for almost a decade, it continues to be held up by the complex, expensive, and time-consuming testing required by the regulatory agencies of various countries. Today, it takes about a decade and somewhere between $10 and $15 million to get a single GM crop to market. Not only is that out of proportion to the market value of specialty crops such as fruits and vegetables, but it's way beyond the means of public sector researchers. So what we've done is we have driven out all of the researchers in the public sector from their traditional roles in helping farmers with their crop problems, except by non-molecular methods. Figuring out how to relax the regulatory stranglehold and achieve broader public acceptance of GMOs are very difficult problems, but they're social and political problems. The science is quite clear. The challenges I outlined earlier to increasing food production are difficult ones, but not impossible. That is, if and only if we can use the most modern scientific methods and findings and translate them into our food production systems. Our current crops need to be made more tolerant to heat, drought, flooding, salinity, pests, and diseases. We must and can do this biologically so that we reduce our reliance on toxic chemicals that kill organisms indiscriminately. We need to increase plants' nitrogen utilization and phosphorus uptake efficiencies so that we can reduce nitrogen and phosphorus pollution of air and water. The deeper challenge, which has yet to be tackled seriously as far as I can tell, is to increase the efficiency with which plants convert solar to chemical energy through photosynthesis. But I frankly think that this will not be enough. I think we have to think seriously out of the box and invest far more in new crops, new methods, and new food production systems. So what do I mean by that? Well, I'm just going to give you some small examples. But first, let's ask how. How do we go about making agriculture sustainable, even as we increase its output? Well, first, and I've already gone over this territory, as I've described, we have to be able to use modern biological methods. These will allow us to create a less chemically driven agriculture, even as we increase yields. But I think it will take a revolution in how we think about agriculture to make it sustainable. We have to start thinking about agriculture as a closed system or a system of systems within which we optimize the use of land, water, and energy to create food, feed, and fiber. In this country, we've optimized for low labor input using very high inputs of water, chemicals, and machinery. Well, frankly, I leave biofuels off the list of food, feed, and fiber, although it's all the rage at the moment. This is because we currently burn something on the order of 400 years worth of photosynthesis every year. Put another way, we now burn about 100 times more calories per person than we eat. The notion that we can expand agriculture to meet a significant fraction of that energy demand from the annual photosynthetic yield while doubling the food supply and reducing agriculture's ecological impact simply defies credulity. Now, I think it's also worth stating that the most efficient agriculture today is in the private sector. If we're serious about feeding more people using less water, energy, and land, we need to put our development resources where they will yield the best return. It has become very fashionable in well-fed, largely urban, developed nations to vilify industrial agriculture and romanticize the smallholder, independent family farmer, both here and in developing nations. But smallholder farmers will not feed a world of 9 or 10 billion, nor will the inefficient methods of organic agriculture. Only when a farmer can grow enough of sufficient value to sell can he or she advance out of poverty. Now, this is very politically incorrect in development circles, but the objectives of food companies, the ones that are so vilified, actually align very well with the objective of sustainable development. Sustainability advocates, of course, often view them as the villains. For example, it behooves Nestle to work with farmers in small cooperatives in developing countries to adopt milking techniques that minimize bacterial contamination, since the bacterial count of raw milk determines the heat treatment needed and therefore the quality of the final product and its commercial value. Conversely, smallholder farmers, particularly in developing nations, profit from such an association because the company is a reliable, recurrent customer. Agricultural development efforts rarely address a complete value chain from the farm to the international market, but companies must increasingly do so. This is my candid view that we need to be less nostalgic and much more practical with our development dollars, seeking to leverage them through the efficiencies of the private sector. So what are the elements of the agricultural system that need rethinking? What we do now is extremely inefficient. We pull nitrogen out of the air using energy and dump it on the land in amounts far greater than plants use, with the result that we pollute our surface and groundwaters. We then feed about half of the grain we grow to animals, many of which expend the vast majority of the input calories on their own metabolic activities, and for the most part, we make little use of the plant nutrients the animals excrete, so they become additional pollutants. Our major crops, corn, wheat, cotton, rice, canola, are extremely water inefficient. All over the world, we use non-renewable water resources to grow temperate crops like wheat with water from fossil aquifers. Here's an example of irrigated wheat production in Saudi Arabia, where it was highly subsidized by the government until recently. Now, state support for irrigated wheat production was removed in 2008, but unfortunately for Saudi Arabia, other crops took the place of wheat, and at the current rate of water withdrawal, it's estimated that the aquifers will be exhausted in 25 or 30 years. That's not much time. Lest you think this is a uniquely Saudi folly, I hasten to tell you that the picture is very similar in our own arid west and southwest, where the Ogallala aquifer is already depleted in places and in others showing a decline in water level of as much as 2 or 3 feet per year. Such practices are doomed because the aquifers are either fossil aquifers that are not recharged at all or recharged more slowly than they're being used. They're also doomed because this kind of irrigation results in the buildup of salts in the soil. Indeed, soil salinization is catching up with irrigated agriculture everywhere in the world. Very gloomy thoughts, but let me tell you that it's not all lost. There's no universal answer, but I'll give you now some examples of more water, nutrient, and energy efficient systems in both open and closed environments. These are fields in Israel that are irrigated underground using pressure-driven irrigation hoses that dispense water and nutrients from a computer-controlled tanks that you can barely see in the distance. This is called fertigation. The objective is to deliver just the water and nutrients needed and just when they're needed, minimizing water use and nutrient pollution, as well as eliminating salt buildup from irrigation. It's all monitored constantly and computer controlled. Now here's an example of an extremely efficient hydroponic lettuce production facility that I just visited a couple of weeks ago in Mirabel, Quebec. It covers many acres, growing lettuce on floating styrofoam rafts, on shallow water tanks, growing lettuce year-round, yielding 5 times the amount per square meter that can be obtained with soil-based seasonal agriculture. Moreover, because the water tanks are completely covered, the only water lost is that attributable to evapotranspiration by the plants. The water's been recycled for years. This facility, too, is computer-controlled. The water quality is constantly monitored, and virtually no chemicals are used for pest and pathogen control. This is a similar lettuce growing facility with a marked difference because it does not use chemical fertilization. Instead, it grows trout in the tanks that you can see under the seed beds here, and uses the water in which the trout are grown to provide essentially all of the nutrients to grow the lettuce. This is a marriage of aquaculture and hydroponic horticulture, and it's called aquaponics. It's in fact a modern version of very old practices developed and used in Asia. Some of the systems in Hawaii are like several thousand years old. Aquaculture today provides about half of the fish that people consume, but much of it remains nutrient inefficient and polluting because the nutrient-rich waste from the fish is not managed and pollutes both fresh and saltwater bodies. The nutrient wastes from fish culture can be managed in open bodies of water, not just in closed aquaculture systems. And then these practices, I think China is quite far ahead of this country. Now, in this particular system, the solids are removed, and then the water is cycled through this tank, which contains a gravel bed with nitrifying and nitrosifying bacteria, which convert the ammonia that the fish excrete into nitrates. Now, there's still a big problem, even with this system, because the feed that is fed to the fish today comprises largely soybeans. So you're harvesting fertilizer from fields. This is not an unsolvable problem, but deserves a lot of attention. In Israel, one of the research institutes had developed a system where farmers can grow their own feed from algae and process it into a form that the fish can use. Now, finally, this is Loofah Farm, a brand new 30,000-foot computer-controlled greenhouse on the roof of an office building in Montreal. It's urban farming at its most original. Its tech-savvy owners dispense nutrients and water remotely by computer from large tanks, increasingly fed by rainwater. And this is hydroponic agriculture, and the nutrients are supplied chemically from these large tanks. This is part of the control system and the monitoring system. This is constantly monitoring water quality. The plants are grown hydroponically, either using something called the nutrient film technique or in soilless flats containing coconut shell medium. Water is recycled, as I said, and water quality is constantly monitored. Biological control techniques are used to control insects and pests, and the picture-perfect vegetables and herbs are delivered to local consumers, minimizing transportation costs. I'd like to underscore the fact that this is an example, that all of these examples that I've given you of agricultural intensification and more efficient use of water and nutrients, none of them qualify as organic. While there's a growing belief that organic and sustainable are one and the same, there is no necessary connection. The organic rule is a set of procedures, among which is a prohibition on the use of synthetic fertilizers. So I've just given you a tiny taste of some of the promising approaches to reducing energy, land, water, and nutrient requirements of food production. I've barely begun. I talked about aquaculture, which is a far more water-efficient method of producing animal protein than poultry and livestock. And yet people like to eat meat. Making meat production more water and nutrient efficient is a significant and multidimensional challenge. Today, we feed close to half of the grain we grow worldwide to animals, which are somewhere between poor and disastrous, have somewhere between poor and disastrous feed conversion ratios, which means that they're also very water inefficient. There are researchers developing direct culture techniques to produce animal muscle tissue for food in tissue culture. Now, this sounds pretty far out at the moment, but it's not impossible. Another promising direction for research is developing feed crops that can be grown on desert land using seawater. While some effort has been invested in developing halophytes, which are salt-tolerant plants, for food and feed, there is still an enormous amount to be done. All of our major food crops today are water-inefficient, temperate crops that don't do well at higher temperatures. The bottom line is that making agriculture sustainable, even while we double the food supply, can be done. But the question is, will we do it? My deepest concern is that galloping urbanization everywhere in the world makes us susceptible to the modern version of Marie Antoinette's let them eat cake syndrome. Or what food problem? I just go to the grocery store. We still invest just pennies of each biomedical research dollar in agricultural research. And we've erected almost impenetrable regulatory barriers to using modern biotechnology for crop, fish, and livestock improvement. Thus, what stands in the way of creating a sustainable agriculture to feed 9 or even 10 billion is us, our unfounded fears and our equally unfounded belief in organic agriculture, as well as our unwillingness to invest the necessary resources. Thank you very much, and I'd be delighted to answer questions. All questions are allowed. You get free 10 dumb questions, and if you run out, you can have 10 more. Yes?
Do you think that the perception of biotechnology is going to change in the near future? And what?
Let me answer one question at a time. I'll come back to that. So the question is, do I think that the perceptions of biotechnology will change in the future? They are changing, little bit by little bit. But not fast enough. I think Africa, in places, is recognizing that it really needs this technology, and it can't be forever in the sway and in the shadow of the anti-GM feelings in Europe. If China actually brings genetically modified rice to market, that may open the floodgates. But I don't know. It's turned out, in the early days of recombinant DNA technology, everybody was very concerned, but in the biomedical area, that lasted for 10 years and it was gone. What would we do today without human insulin produced by recombinant DNA technology? But in this area, it's lasted now for 30 years. It's really amazing. Once a cocoon of fear has wrapped around something, and then it goes on the internet, of course we have now enormous amounts of misinformation on the internet, it's pretty hard to dispel. But I go back to a previous example because things can change in a hurry. When I was writing my book, Mendel in the Kitchen, I was in correspondence with a man by the name of Don Duvek, who's since died. He was the head of plant breeding at Pioneer. And he wrote me this wonderful little message. He said, you know, back when he grew up on a farm, and he said, my dad was really, he really paid attention to things. And everybody was skeptical about hybrid corn because they'd be beholden to companies and they'd have to buy their seed every year. And you hear that over and over and over again about having to buy seeds from companies. He said, until the drought in 1936, I think it was, came along, and the only thing worth bringing in was the hybrid corn. And then he told me that his dad was curious. The professors all said, you can't grow this corn again because hybrid vigor is a function of the first hybrid generation. So he planted some out. And he said, well, my dad concluded the professors were right. And today, it's accepted that people buy seeds because they get higher yields. And yet, in many places, this has become one of the reasons that people are so angry at companies. Gee whiz, we'll have to buy seeds. Well, the farmers aren't dummies. They migrate to this not because anybody's forcing them to buy it. It's because it yields better. Your second question. Actually, it was a fairly short seminar, so I think we had plenty of time. No, but she had another question. I think there's enough time.
So it seems like scientists have done a good job at producing decent technology and biotech, and that the hurdle is actually policy. And from your perspective with politicians and international policy, can you give us any glimpse into the book there? Is that ever going to change? Is that ever going to change?
The question is that I've communicated the fact that the real barrier is policy, politics, but I would add also personal attitudes. Attitudes that people are afraid that if they, and I've heard this today 14 times, they're afraid that marketing GMO would be the kiss of death. You know, and organic is all the rage. Yes, it is changing. Now, one of the reasons that I took the job in Washington was I figured that I would have some impact. I worked really hard on this issue. There is a high-level group that is convenient to address this question under the Office of Science and Technology Policy, which is the White House office that brings together the agencies. I keep on pushing on it. Roger Beachy, who is the head of National Institute of Food and Agriculture, has resigned his position for personal reasons, but he's going to continue working on this issue. I don't know how much. If you talk to the regulators, they say, what's the problem? They should come and talk to us. But the problem is that it's so costly. Okay, and you can't, it has to be economically feasible. If it costs you $15 million and it'll take you 150 years to recoup that investment, you're not going to do it. So this regulatory nonsense, and it evolved for all the right reasons, but the wrong outcome. The original committee that was put together under OSTP that issued guidelines back in 1987 said, gee, we don't see any new hazards coming out of this technology, so agencies, you go and regulate under the laws you have. Well, the EPA regulated under Toxic Substances Control Act, for heaven's sake, and the Federal Insecticide, Rodenticide, and Fungicide Act. These are all toxic chemicals. You know, no wonder everybody's scared. And then there are 3 agencies. You have to go to USDA, you have to go to EPA. So bringing this together under one roof, now India has done that. So there is hope, and there are new regulations bit by bit wending their way through the legislatures, particularly of African countries. Part of the problem is that there's no regulatory framework, there's no regulatory experience. The African Union is training people, so there is hope. It just is slow. There was one here, 2, 3, and 4.
Related to what you just said, because also the opposition in Europe is also to some extent driven by the high cost of doing the regulatory approval for minor crops.
And the question?
Well, the question was what was your thought about the high cost of the regulatory process for transgenic crops, what you already mentioned.
Right. Now, Europe, interestingly enough, so the question is, what about Europe? So in spite of the complexity, so Europe instigated a system that was aimed directly at this contemporary genetic modification, and required the approval of all the member states. Now, in spite of that complexity, a number of regulatory approvals were issued in the late 80s, early 90s. And then it stopped. And that was the point at which there was a moratorium on genetic modification, and it's never recovered since then. And it affected the pipeline of innovations worldwide. 2, 3, 4. 2.
How do you think the issue of coexistence between organic and genetically engineered crops is going to play out?
Can I answer? So the question is, how is the coexistence between organic and genetically engineered crop going to play out? If I had a crystal ball, I'd be really happy. I'll tell you what I think. My personal view is we have to take what organic has brought to us, which is a really great, much greater attention to maintaining soil fertility and all that stuff. But I say throw away the rule book and use the most modern science. Take the best of all of that consciousness of the need to sustain soil quality. But just to give an example, since genetically modified organic farming still involves plowing, and that, of course, is a major soil erosion factor. The biggest contribution to decreasing soil erosion has been the development of the combination of genetically modified, herbicide-tolerant soybeans and no-till farming. I mean, that's what we need. So that's an example. That accomplishes the goal of preserving soil fertility, and yet uses the, so the objectives. The principle is important. We need to use less exogenous nutrients. We need to make better use of the nutrients that are thrown away by the fish, the poultry, the animals that we feed, but we have to do it with modern science and not with techniques that were developed a century ago. Wait a second, am I right? Yeah.
So how much do you think the resistance to GMO arose from the first traits that people put in? For example, the first one was a toxin, as you mentioned, and then Roundup Ready, where you put more chemicals, apply more chemicals than you would if you have a weed.
So the question is, to what extent do I think that the resistance to GMOs arose from the original traits that were used?
We had initially engineered drought tolerance.
Well, let's look at it from a historical perspective. I think if anybody had walked into given that the primary method for accelerating plant breeding in the 20th century was chemical mutagenesis and radiation mutagenesis. Anybody that would walk in, and we planted out all these irradiated things with unknown mutations of all kinds, and nobody worried about it, nobody regulated it, and there were no disasters, okay? There were a few crops that were produced that were selected for, higher insect resistance that turned out to be pretty toxic because they had higher alkaloid or sorolin concentrations. So in that, and nobody, it wasn't an issue. And the first traits that were selected for being pretty innocuous. People had used the raw bacterium, Bacillus thuringiensis, which accumulates this protein, which is toxic to insects but not to people, for many decades. It's perfectly okay in organic agriculture to spray the bacterium, but it's not okay to have a plant that produces a little of this innocuous protein. And by the way, the first version of the organic rule did include the use of genetically modified crops because the USDA was also fairly confident that there wasn't anything terrible in the techniques. Okay, so if you'd walked into a boardroom of Monsanto or whatever in 1970, whenever they started this research, and said, well, you guys have got to be really careful because if you don't use the right traits and make it good for consumers, you're going to be in big trouble. They would have been laughed out of the room because this kind of improvement for farmers, that's what plant breeders did, for heaven's sake. So I think it's really nice, and hindsight is 20/20, but that's the problem.
Resistance is that initial
I think there are so many origins of the resistance that a single causative attributing, and that, the companies have been accused, Monsanto particularly, of over-proselytizing and being very enthusiastic. Another reason is they call genetic engineering. Well, gee whiz, we engineer buildings and cars, but we don't engineer crops. There's a whole bunch of them. And then in the UK, the early, there was a fellow by the name of Pushtai that fed genetically modified ricin-expressing potatoes to rats, and he concluded that they were getting sick. Now, his data, he admitted, I met with some members of parliament when I was there a couple years ago, and they said when he testified in parliament, he admitted his data were not reproducible and not. But he's made a career out of going around the world, and this was when the first supermarket chain, they were on the GM I think canned tomatoes were already on the shelves, and the first, food chain that said we're going GM free was followed by a stampede of others. And so, those are the sort of the critical things. I can hardly blame that on Monsanto. So there are lots of reasons. And this is a very fertile area for like the Terminator technology, which is an urban legend, but everybody believes it's true. Go ahead.
So you mentioned that large agriculture, efficiencies of scale and all that makes sense, that that's the most efficient way to.
I'm afraid it's here to stay.
But recently Bill Gates just came out with this thing that said a small farmer can do it. I'm wondering, how do you reconcile these policies?
It's very popular to say that now. But the fact is that 20% of the world's farmers produce 80% of the food. Now, it's not the case that small farmers can't find a niche. This urban greenhouse is going to make money, and it's a two-person operation, And if you go to the DuPont Street Market in Washington, you come away with a little bag of produce for $60. Somebody's making money. But that isn't going to feed the world. Okay, so there's no one solution, but I think there are lots of solutions, but I think the big problems are water efficiency, and we're not working on that much. They're nutrient utilization. How do we decrease pollution and increase the amount of the nitrogen that we harvest gets used? These are major problems. Yes?
I have a question. So thank you for the great piece. And in Hollywood, they make all these movies and
yes, they do.
in the developing country. And the impression they have there is the developing country, the rich people are eating organic food. And they dump all this GM food to a developing country, which try to eliminate the human growth there. Do you think if this idea is going into everyone's mind because they watch a movie and they watch on the TV, it will become even bigger wave of anti-GM in the developing countries?
That's happening now. By this time, it should have been subsiding, but it isn't. And indeed, the whole marketing, the belief structure around organic as superior nutritionally, which it isn't. Frankly, plants don't care if they get their nitrogen from poop or from a bag of fertilizer, as long as it's in the right chemical form. But it is a less efficient form of agriculture, and it has to charge higher prices, so it's not a bad marketing ploy to convince you that it's better for the land, it's better for you. And frankly, there's an element of truth in places to those organic agriculture assertions, because there is more attention paid to maintaining soil quality in many places, particularly in the developing world, in organic production compared with chemical production. Now, that's not universally true, and there are lots of very big industrial farms that are very, very attentive to soil, to maintaining the soil and to doing things in a sustainable way. So, yes, the urban mythology does drive people. The sad part is that people really act on this belief structure. But, frankly, if you go to Whole Foods, which in many places is called the whole paycheck store, you find that very little of the produce is actually organic. It's just very high quality, expensive, good produce. So, sorry, but I can be shot for being anti-organic, but these are the facts. Okay, I think we've exhausted it. And me?
Please join me in thanking Nina for a great talk.